Okay, so what I wanted to highlight, this is something that is important in stochastic simulation. And I'm going to show it with an example here, which is a system that is bistable. In the deterministic version, I'm showing here when I have a high value of initial concentration, it goes to this steady state. If I decrease it, I have a slider, it goes to the other concentration. And so depending on how high the concentration is, it goes to one or the other. Now, if I run this simulation stochastically and in COPASI, that is basically simply selecting a stochastic solver here. I'm going to use the direct method, which is the standard Gillespie algorithm. And now you run the simulation, you see it's not only stochastic, but it, of course, it went to the right steady state. So steady state is now an oscillation around it. But the second one is also in the same steady state, but it's different. So it's almost like if you run one version of this stochastic simulation, that one alone is not enough. It doesn't really tell you much. It's one instance of the draw of the random numbers. So I can run another one and I can run another one. What I really want is a histogram of the probability in which the concentrations end up at a certain value. And in this system, by the way, as you could see just now, when it's stochastic, because it's bistable, sometimes it goes to one steady state, sometimes it goes to the other. So as you can see, sometimes it's going below, sometimes it's going above. So what I want to do is I want to run many simulations to find out what is the average behavior of the system. So let's do that in this case. I just go to parameter scan and I want to run the time course. When you select time course, it of course runs the time course exactly what it was selected here, the time and the algorithm. So I want to do that, but I want to actually create just a repeat. I just want to run this same thing with the same parameter values many times, which is repeat. So I create repeat and I'm going to run 100, which is pretty quickly. So if now I press the run button, what you see is that it actually is showing the system progressing, and sometimes it goes in one steady state, sometimes it goes in the other. And just looking at this plot is okay. It shows you the level of oscillations, but maybe we just want to know the kind of steady state behavior of this system. So we want to cut out this first part. Let's say, let's cut out the first 15 seconds. That is something we can do in time course by saying suppress output. We turn on this part, suppress output before 15. So now if I go back and I run the same thing again, you won't see the first 15 seconds. So you just see the system ending up in one steady state or another, and how much variability exists in each one and in the other one. But again, this time course plot is informative, but actually the larger the number of repeats, the less informative it is, because it starts becoming very dense. So what you want to do is that you want to actually draw a histogram of the times that the concentration ended up in each one of these values. And that's something in COPASI that you can do in the plots. I've created a plot here. And when you do, basically I'm gonna remove this and show it again. We create a new plot. In this case, rather than plotting a curve, I want to plot a histogram. When you plot a histogram, you have to select just one variable. In this case, the variable is my species. So I want the concentration of that species, X, and you'd select a bin size. In this case, because it's particle numbers, there's no point in having a bin size smaller than 1 because it's always integer values. So that's the smallest bin size. And you can change the title or not. So now I go back and run my scan again. And what you see is that in this plot here that appears, this is the histogram. So this now shows you the distribution of concentration. So you can see that this is the low concentration, the low steady state, the one that's around here, around 100. And that's the high steady state. And this gives you the probability in which these things end up in both. So the important thing about stochastic simulations is that you have to usually run many times a stochastic simulation. And parameter scan is a good way, or in this case, it's just a repeat. We can run even more. And the more you run, the better the distribution will look like, the smoother, because of course you're accumulating more samples out of out of it. So this is basically running all those 1,000. I mean, it's run 190 by now, 200 and so on. So that's the one thing I wanted to highlight for stochastic simulations, that running one is usually not what you want. You normally want to run many and look at statistics of many simulations. In this case, it's a very simple histogram to show the steady states, basically.
Well, maybe you can point out that if you use that set of parameters deterministically, it won't show you that behavior at all. It'll only show you the lower concentration, right?
Exactly.
So sometimes there is a qualitative difference between a stochastic simulation and a deterministic simulation that you just won't appreciate.
Yeah, so if I show again just the time course, if I choose the deterministic and I run it, it went to my lower steady state. And if I run it again, it's always in the lower steady state. In fact, the solution is just recalculating the same thing. If I change the parameter a little bit higher, then it goes only to the top level. If I run this, it will give me only the top level. And if it's right in the middle, in the transition, there's a bifurcation, of course, which is a transition from one to the other here, or we're on the separatrix. That's basically what it is. But now we're very close to it. So if I run the stochastic close to it, what it happens is that it not only does it go to one or the other, but sometimes it even jumps from one to the other. So sometimes it's low, sometimes it's up and then goes low, which you also get to see in the parameter scan. When you run the parameter scan, sometimes you see one that is above and then eventually ends up below. It's not incredibly common. It's a low probability event, but it does happen. In this case, so far, the luck of the draw, it hasn't shown it, but when I tested this, I actually had two of them that were, so this one crossed. This was low and it went up. And sometimes you see one also doing the opposite. But it's a very low event, of low probability. There's a final question there again. It looks like, is there a time limitation and species number limit for running VCL in a server?
Yes, there is a time limit because otherwise you will hang up the system. And species numbers...
Wait a minute, there's no time limit.
No, we have a time limit for 2
hours.
Yeah,
21 days.
21 days?
Your simulation cannot run for more than 21 days on the cluster.
Really? I've run longer ones. But you can, if you need to, you can get special permission to run longer.
Yeah.
But 21 days is pretty long.
Yeah.
But you can run multiple simulations during that time. You're not limited to one simulation. So you can run, I think the number of simulations you can run simultaneously is
100.
100, yeah.
Yeah. But again, if you...
very few people need 21 days to run a simulation. Most of them are over in a few minutes to an hour or two, depending on what it is.
Yeah. Generally, your model should be easy first. You can expand it later more and more and more. But you never start your modeling with something that runs hours.
And note that for VCell, at least just like in COPASI, you can see there, you can see things happening before your thing is complete. Even when you send it to the server, you can get partial results back. So, you know, you can figure out if you've messed up something early on before you've let it run for 21 days by looking at the first couple of results that come out and realize you've set something wrong or done something incorrectly. So it's always a good idea to check, but you can get data back before the simulation is complete.